Welcome! In this video, we'll explore LeetCode problem number 1719, number of ways to reconstruct a tree. This is a fascinating and challenging problem that combines concepts of graph theory and algorithm design. We'll break it down step by step, discuss various approaches, and analyze the complexities to help you master this topic. Let's dive in. In this problem, we are tasked with reconstructing a binary tree from an input array called pairs. Each element in pairs represents an undirected edge between two nodes. A valid reconstruction of the binary tree must satisfy three key conditions. First, the tree must contain exactly n nodes, where each node is uniquely labeled from 1 to n. Second, the tree must be rooted at node 1. Third, the given pairs array must accurately describe all the direct parent-child relationships in the tree. Based on these conditions, the goal is to determine how many valid reconstructions of the binary tree are possible. The output can be 0 if reconstruction is impossible, 1 if there is a unique valid reconstruction, or 2 if there are multiple valid reconstructions. The input consists of a list of pairs, where each pair defines an undirected edge, and the output is an integer representing the number of valid reconstructions. To understand this better, let's look at the first example. Here, the input is pairs equals 1, 2, 2, 3. The output is 1, indicating that the binary tree can be uniquely reconstructed. The reconstructed tree has node 1 as the root, with node 2 as its child, and node 3 as the child of node 2. In other words, the structure of the tree is a straight line, starting from the root 1 and going down to 2, and then to 3. Since this structure aligns perfectly with the given pairs and there's no alternative configuration, the output is 1, meaning there is exactly one valid way to reconstruct the tree. Now let's examine another example, where the input is pairs equals 1, 2, 2, 3, 1, 3. This time, the output is 2 because the binary tree can be reconstructed in two different ways. In the first possible tree, node 1 is the root, and it has two children, nodes 2 and 3. This structure satisfies the given pairs, as 1 connects to both 2 and 3, and 2 connects to 3. In the second possible tree, the structure is a straight line, similar to the first example. Here, node 1 is still the root, but node 2 becomes the child of 1, and node 3 becomes the child of 2. Since both of these configurations align with the input pairs, there are two valid reconstructions of the binary tree. Therefore, the output is 2, indicating multiple valid reconstructions. Now let's consider the third example, where the input is pairs equals 1, 2, 2, 3, 2, 4. The output is 1, meaning the binary tree can only be reconstructed in one unique way. In this tree, node 1 is the root, and node 2 is its child. Node 2 then has two children, nodes 3 and 4. This structure matches the input pairs exactly, and no other valid configuration is possible. That's why the output is 1, indicating a unique reconstruction. Finally, it's important to note some additional details about the problem. A valid binary tree must follow strict properties. Each node can have at most two children, there must be exactly one root with no parent, and every other node must have exactly one parent. When solving this problem, it's essential to validate these properties while handling edge cases such as disconnected graphs, cycles, or nodes with multiple parents. By carefully analyzing the input pairs and ensuring these properties hold, we can determine whether the tree can be reconstructed, and if so, whether the reconstruction is unique or has multiple valid configurations. To solve the problem of reconstructing a binary tree from the given pairs of edges, we need to carefully consider the constraints and properties of a rooted tree. A tree is defined as a connected, acyclic graph with exactly n1 edges for n nodes. The challenge lies in the fact that the input pairs are incomplete, meaning not all edges are listed explicitly, which makes the reconstruction non-trivial. One approach we could consider is a brute force method. In this approach, we enumerate all possible subsets of edges from the given pairs and attempt to construct a graph for each subset. We then validate whether each graph satisfies the conditions of a rooted tree. However, this method is computationally expensive. With input sizes of up to 10 to the power of 4, the number of subsets grows exponentially, making this approach infeasible for larger inputs. Another approach involves graph-based reconstruction with validation. Here, we use the properties of a tree and the constraints provided by the pairs to incrementally build and validate the graph. A key observation is that a valid tree has exactly n1 edges, and there must be a single root node with a degree greater than 1. This method is more structured than brute force, but it still has room for improvement in terms of efficiency. Building on the graph-based reconstruction approach, we note that for the graph to form a valid binary tree, all nodes must be connected, and cycles must be avoided. To implement this, we can start by calculating the degree of each node based on the given pairs. Nodes with the highest degrees are potential candidates for the root. For each candidate root, we attempt to reconstruct the tree by performing a breadth-first search, BFS, or depth-first search, DFS, to check connectivity and ensure there are no cycles. During this process, we validate the structure to ensure it adheres to the binary tree properties. The number of valid reconstructions is then counted based on these validations. While this approach is significantly better than brute force, it requires iterating over all potential roots and performing repeated validations. This redundancy increases the computational overhead, especially for larger inputs. To address these inefficiencies, we turn to an optimized approach that leverages the hierarchical structure of the tree. In this optimized method, we make the key observation that the root node must have the maximum degree and that parent-child relationships between nodes can be inferred directly from the degrees and the structure of the pairs. The optimized graph reconstruction approach begins by identifying the root node, which is the node with the highest degree. Using the given pairs, we infer parent-child relationships to build the tree structure incrementally. This process avoids reconstructing the tree multiple times by pruning invalid cases early. Once the tree structure is inferred, we perform BFS or DFS to validate the tree in a single pass. This includes checking that the reconstructed tree matches the input pairs and counting valid reconstructions. The computational complexity of this approach is O(n plus m), where n is the number of nodes and m is the number of edges in the pairs. This makes the approach highly efficient compared to earlier methods. However, one limitation is that it assumes the existence of a unique root node. In cases where multiple roots are possible, additional checks are needed to handle such ambiguities. Despite this, the optimized approach strikes a good balance between correctness and performance, making it suitable for solving the problem efficiently even for the largest inputs. When comparing the different approaches, the trade-offs become clear. The brute force approach, while conceptually simple, is far too slow for large inputs due to its exponential time complexity. Graph-based reconstruction with validation is more structured and avoids the exhaustive enumeration of subsets, but it still involves redundant checks for multiple candidate roots, which can be computationally expensive. The optimized reconstruction approach, on the other hand, is both efficient and tailored to the problem's constraints. By leveraging key properties such as node degrees and the hierarchical structure of the tree, it avoids unnecessary computations and ensures scalability. However, it does require careful handling of ambiguous cases, such as when the root is not unique. Overall, the optimized approach provides the best balance of efficiency and correctness, making it the most practical choice for solving this problem within the given constraints. In this problem, we need to determine the number of valid rooted trees that can be reconstructed from a given list of pairs, where each pair represents an undirected edge between two nodes. A valid tree must satisfy three key properties: it must be a connected acyclic graph with exactly one root, it should be uniquely identifiable from the given pairs, and if multiple valid trees exist, we need to account for all possibilities. To solve this, we can break the process into clear steps. First, we verify the input constraints. This involves extracting all unique nodes from the pairs and determining the total number of nodes, denoted as n. A valid tree should have exactly n1 edges, so we check if the number of pairs provided is sufficient to form a connected graph. Next, we calculate the degree of each node. By counting the number of edges connected to each node, we can start to identify potential root candidates, as a root typically has the highest degree. This initial setup ensures that we meet the basic requirements for constructing the tree. After verifying the constraints and counting node degrees, the next step is to identify potential root candidates. A valid root should be a node that connects to all other nodes in the tree, and this can be determined by examining its degree. If no such root candidate exists, we can immediately conclude that constructing a valid tree is impossible. Once we have potential root candidates, we construct an adjacency list to represent the graph. This is a key step as it allows us to efficiently traverse and validate the tree structure. Using the adjacency list, we then perform a BFS or DFS starting from a root candidate. This traversal ensures that the graph is both connected and acyclic. Additionally, we verify that every edge in the tree corresponds to a pair from the input. If any edge is missing or invalid, the tree cannot be constructed. Finally, we count and verify the number of valid trees. If the graph satisfies all the required properties, we increment the count. In cases where multiple root candidates exist, we repeat the validation process for each candidate. One of the most important insights in this problem is the need to check both the validity and uniqueness of the tree. For the tree to be unique, its hierarchical structure must align exactly with the given pairs. Identifying the root node is a critical part of this process because the root determines the overall structure of the tree. Nodes with the highest degree naturally stand out as potential root candidates, making the degree calculation step crucial. Using an adjacency list is particularly efficient for representing the undirected graph formed by the pairs, as it allows for quick traversal and validation. Additionally, maintaining a dictionary to store the degree of each node helps us efficiently identify root candidates. These data structures play a central role in ensuring the algorithm runs efficiently while meeting the problem's requirements. To further support the algorithm, we use a set to track visited nodes during traversal. This ensures that we can detect cycles and verify that all nodes are reachable, both of which are essential for a valid tree structure. From a complexity perspective, the time required for the solution is O(n), where n is the number of edges in the input pairs. This accounts for constructing the graph, calculating degrees, and performing BFS or DFS traversals. The space complexity is also O(n), as we need to store the adjacency list, degree dictionary, and visited set. Several edge cases need to be considered to ensure robustness. For example, a disconnected graph, cycles during traversal, or the absence of valid root candidates immediately invalidate the tree. Similarly, if the number of edges is insufficient, the graph cannot form a tree. Optimizations such as early exits during validation can improve efficiency, particularly when the graph fails basic checks like the node or degree count. Using BFS instead of DFS can also be advantageous for detecting connectivity issues in large graphs more quickly. Here, we begin by importing the necessary modules, defaultDict to simplify the adjacency list construction and deque, which may assist in other operations as needed. In the checkways method, we start by building the adjacency list from the given pairs. Each node is mapped to a set of its connected neighbors, ensuring efficient lookups. Next, we sort the nodes in descending order of their degrees, or the number of connections they have, since nodes with higher degrees are more likely to be closer to the root in a valid tree structure. The first node in this sorted order is assumed to be the root. We then validate this assumption by checking if the root connects to all other nodes. If it doesn't, we immediately return 0, as no valid tree can be constructed. We also initialize a flag, multiple_ways, to track whether there are multiple valid tree configurations. This setup prepares us to iterate over the nodes and determine their parent-child relationships. Now, as we iterate through the nodes sorted by degree, we look for the parent of the current node. The parent is chosen as the neighbor with the smallest degree that is still valid, meaning it appears in the ordered node list. If no such parent exists or if the current node's neighbors are not a subset of the parents, the tree structure is invalid, and we return 0. Additionally, if the parent and current node share the same degree, it indicates that multiple valid parent-child relationships are possible, so we set the multiple_ways flag to true. After processing all nodes, we return 2 if multiple configurations are possible or 1 if the tree is uniquely determined. This implementation efficiently checks the tree reconstruction conditions while handling edge cases like invalid structures or ambiguous relationships. In this implementation, we start by building an adjacency list from the given pairs. Each pair represents an edge between two nodes, so we ensure each node is mapped to a set of its neighbors. Using a hash map, we add both nodes of each pair to the adjacency list, creating a bidirectional connection. Once the adjacency list is complete, the next step is to sort the nodes by their degree, which is the number of connections each node has. This is done in descending order so that nodes with the highest degree come first. After sorting, we identify the root node, which should be the node with the highest degree. For a valid tree, the root node must connect to all other nodes directly, so we check if its degree matches the total number of nodes minus 1. If this condition fails, we immediately return 0, as the tree structure would not be valid. The variable multiple ways is introduced to keep track of whether there are multiple valid ways to reconstruct the tree. As we move into the main logic, we iterate through the nodes in the order of their degrees. For each node, we retrieve its current neighbors from the adjacency list. The goal is to identify the parent of the current node, which should be a node with a higher degree that appears earlier in the sorted list. To find the parent, we iterate through the neighbors and look for the one with the smallest degree among the eligible candidates. If no valid parent is found, or if the supposed parent does not contain all of the current node's neighbors, we return 0, as this would indicate an invalid tree structure. Additionally, we check if the current parent has the same degree as the current node's neighbors. If this is the case, it implies that there might be multiple valid parent-child relationships, so we set the multiple ways flag to true. This ensures that we account for scenarios where more than one valid tree structure exists. Finally, we return the result based on the multiple ways flag. If multiple valid parent-child relationships were found, we return 2, indicating that there are multiple ways to reconstruct the tree. Otherwise, we return 1, signifying that there is only one unique way to build the tree. This concludes the implementation, ensuring that we handle all edge cases and verify the validity of the tree structure while accounting for the possibility of multiple solutions. To begin reconstructing the tree, we first take the input pairs 1, 2, 2, 3, and build an adjacency list. The adjacency list is a dictionary where each key represents a node and its value is the set of nodes it directly connects to. We start by initializing an empty adjacency list. Processing the pair 1, 2, we update the list to show that node 1 connects to node 2 and vice versa, adj equals 1, 2, 2, 1. Adding the next pair 2, 3, we expand the adjacency list further, adj equals 1, 2, 2, 1, 3, 3, 2. Next, we sort the nodes by their degree, which is the number of neighbors each node has, in descending order. Here, node 2 has the highest degree of 2, while nodes 1 and 3 each have a degree of 1. The sorted order becomes 2, 1, 3. We then evaluate if node 2 can serve as the root. Since node 2 connects to 1, 3, and this matches the total number of other nodes in the graph, we confirm that node 2 is a valid root candidate. With the root confirmed as node 2, we proceed by iterating through the nodes in descending degree order. Starting with node 2, its neighbors are 1, 3. Since node 2 is the root, there's no parent node with a smaller degree to consider. Moving on to node 1, we see that its only neighbor is node 2. The parent of node 1 is determined to be node 2. We then verify if 2, the neighbors of node 1, is a subset of adj 2, the neighbors of node 2. This condition is valid. Similarly, for node 3, its only neighbor is node 2, so its parent is also node 2. Again, checking if 2 is a subset of adj 2 confirms validity. Since no node has multiple parents and the structure adheres to the tree properties, we determine that the tree can be reconstructed uniquely. The final result is 1, indicating one valid reconstruction. In the next example, we take the input pairs 1, 2, 2, 3, 1, 3. The first step is to build the adjacency list. Processing the pair 1, 2, we get adj equals 1, 2, 2, 1. Adding 2, 3 updates the list to adj equals 1, 2, 2, 1, 3, 3, 2. Finally, incorporating 1, 3, the adjacency list becomes adj equals 1, 2, 3, 2, 1, 3, 3, 1, 2. Next, we sort the nodes by their degrees. Here, all nodes 1, 2, and 3 have a degree of 2, so the sorted order is 1, 2, 3. We then evaluate if node 1 can be the root. Since it connects to 2, 3, and this matches the total number of other nodes, node 1 is a valid root candidate. Now, we begin iterating through the nodes in degree order. Starting with node 1, its neighbors are 2, 3. As the root, it doesn't have a parent to consider. Next, we examine node 2, which has neighbors 1, 3. The parent of node 2 is determined to be node 1. We check if 1, 3, the neighbors of node 2, is a subset of adj 1, the neighbors of the root. This condition is valid. Similarly, for node 3, its neighbors are 1, 2, and its parent is also node 1. Verifying that 1, 2 is a subset of adj 1 confirms validity. However, when we consider multiple reconstructions, we observe that nodes 2 and 3 could potentially swap roles as parent and child. This possibility means that the tree can be reconstructed in more than one way. As a result, the output is 2, indicating 2 valid reconstructions. For the final example, the input pairs are 1, 2, 2, 3, 4, 5. We begin by building the adjacency list. Processing 1, 2, we get adj equals 1, 2, 2, 1. Adding 2, 3 updates it to adj equals 1, 2, 2, 1, 3, 3, 2. Finally, incorporating 4, 5, we obtain adj equals 1, 2, 2, 1, 3, 3, 2, 4, 5, 5, 4. Sorting nodes by degree, we find node 2 has the highest degree of 2, while nodes 1, 3, 4, and 5 each have a degree of 1. The sorted order is 2, 1, 3, 4, 5. Evaluating if node 2 can serve as the root, we see it connects to 1, 3, but does not connect to 4, 5. This breaks the requirement that the root must connect to all other nodes in the tree. Since no valid root exists, the structure cannot form a single connected tree. The result is 0, indicating that reconstruction is not possible. Here, we begin analyzing the time complexity of the solution. First, we focus on building the adjacency list. The input consists of m pairs of nodes, and for each pair, u, v, we add u to the set of neighbors of v and vice versa. Since adding an element to a set is an O(1) operation, processing all m pairs results in a total time complexity of O(m) for constructing the adjacency list. Next, we sort the nodes by the size of their adjacency sets, or degrees, in descending order. With n unique nodes, the sorting step takes O(n log n), due to the time complexity of timsort, the algorithm used in Python for sorting. Together, these steps lay the foundation for the algorithm's efficiency. Now, we move to the next steps of the algorithm. First, we iterate through the nodes sorted by degree to validate the tree structure. For each node, we examine its neighbors to determine the parent with the smallest degree. Since the size of the adjacency set corresponds to the node's degree, and the maximum degree in the graph is O(n), iterating through all nodes and their neighbors results in a time complexity of O(n squared) in the worst case. Additionally, we perform subset validation to ensure the neighbors of each node form a subset of the parent's neighbors. This subset check for each node also has a worst-case complexity of O(n), and across all nodes, this step contributes another O(n squared). Combining these steps, the overall time complexity is dominated by the O(n squared) operations in validation and subset checks, leading to a total time complexity of O(n squared). Shifting our focus to space complexity, the solution requires space primarily for the adjacency list, which is stored as a dictionary where each node maps to a set of its neighbors. The space needed for this structure depends on the number of edges, m. In the worst case, where the graph is complete, m is O(n squared), making the adjacency list require O(n squared) space. The list of nodes for sorting adds another O(n) space, but sorting itself does not use additional memory. Finally, other variables such as those for tracking tree relationships and degrees require only constant space, O(1). Combining these factors, the total space complexity is O(m), which simplifies to O(n squared) in the worst case. Let's compare the algorithm's complexity to a brute force approach. A naive solution would involve generating all possible tree structures and testing each against the input pairs to check for validity. However, because the number of potential tree structures grows exponentially with n, this brute force method would have an impractical time complexity. In contrast, the optimized algorithm leverages constraints like degree-based ordering and subset validation to systematically and efficiently reconstruct the tree. This brings the time complexity down to O(n squared), which is a significant improvement. Given the problem's requirements, further optimization is unlikely without additional insights specific to the problem. Finally, let's analyze the best, average, and worst-case scenarios. In the best case, where the graph already satisfies the tree structure requirements and validation is minimal, the complexity reduces to O, n plus m, which is dominated by the adjacency list construction. In typical cases, the complexity is O, n squared, due to the subset validation and degree-based checks. In the worst case, for dense graphs with O, n squared, edges, both time and space complexity reach their maximum of O, n squared. Mathematically, the adjacency list construction takes O, m, sorting nodes takes O, n log n, and validation contributes O, n squared. The dominant term is O, n squared, making it the overall time complexity. Similarly, the adjacency list, which requires O, m, space, dominates the space complexity. Thus, the algorithm is both time and space efficient within the constraints of the problem, achieving optimal performance with O, n squared, complexity. When tackling this problem, there are several common mistakes to watch out for. First, misunderstanding the problem statement is a frequent pitfall. It's important to recognize that the input pairs represent adjacency information between nodes, not the actual edges of the tree. Assuming otherwise may lead to incorrect reconstructions. Second, always ensure that your algorithm respects the unique tree property, which requires that a valid binary tree has exactly one node that serves as the root. This node typically has the maximum connections, and failing to identify it accurately can break your solution in edge cases. Third, overlooking cycles is another common error. Remember, a tree must be acyclic, so your reconstruction process needs to actively check for and eliminate any cycles that might form. Fourth, inefficient graph traversal techniques, such as redundant operations or poorly optimized adjacency list handling, can significantly impact performance, especially with larger inputs. Finally, edge case handling is critical. Scenarios like disconnected graphs, invalid inputs, or minimal cases such as a single pair can easily cause runtime errors or incorrect results if not accounted for properly. This problem is a favorite in interviews because it tests key graph theory concepts. You'll need to demonstrate a solid understanding of adjacency lists, node degrees, and tree properties like being acyclic and connected. Strong foundational skills in DFS and BFS are essential here, as these traversal methods are commonly used to validate and explore the graph structure. Interviewers also value explainable optimization. Be prepared to articulate how you reduce complexity in your solution, such as efficiently determining the root node by analyzing the degrees of the nodes. Another important aspect is edge case analysis. You should confidently explain how your algorithm handles scenarios like single node trees, disconnected input pairs, or other invalid inputs. Lastly, if you use multiple approaches, such as DFS versus BFS, make sure to discuss the trade-offs. For example, DFS may be more memory efficient in certain recursive implementations, but BFS can often be easier to debug and follow. If you want to deepen your understanding, there are several related problems worth exploring. For example, LeetCode 310, minimum height trees, involves reconstructing or analyzing tree structures based on node degrees, which shares similarities with this problem. Another relevant problem is LeetCode 261, graph valid tree, which focuses on verifying whether a given graph satisfies the properties of a tree. LeetCode 323, number of connected components in an undirected graph, is helpful for building intuition about connectivity in graphs. Finally, LeetCode 1361, validate binary tree nodes, is a great exercise for understanding and validating binary tree properties. In terms of alternative approaches, both DFS and BFS are viable options for graph traversal and connectivity checks. While BFS is often easier to debug, DFS can be more memory efficient, especially in recursive implementations. Another approach is using a union-find data structure, which efficiently detects cycles and checks connectivity. However, union-find may not be as intuitive when reconstructing the actual tree structure. Alternatively, analyzing node degrees and adjacency relationships directly can help you identify potential roots and validate the tree structure. This method is efficient but requires careful treatment of edge cases to avoid errors. Great job! You've now gained valuable insights into solving number of ways to reconstruct a tree. Remember the importance of graph theory and edge case analysis in such problems. Keep practicing and exploring more challenges to strengthen your problem-solving skills. Thanks for watching, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!